Here is the first day of Conic Systems. So if you notice, the book assignment that you have only has 3 problems, 3, 7, and 11, so that shouldn't be too bad. And then in the same section, there'll be more homework problems with tomorrow's lesson. So again, I suggest that maybe you watch both videos so that you can, on Thursday in class, you'll have all the homework questions maybe that you've attempted and being able to ask me some questions. So look at this, my little thinking face here. My little thinking face is here because hopefully you recognize that this is an objective from Algebra 1 and from our first unit, right? It's first unit, second unit, linear equations, right? Solve the system. Remember, system means more than one. And we started with just linear equations. Now remember, we know now that lines are actually a degenerate conic. You can think about that, right? But we don't bother. It has its own unit, linear equations. So except for vertical lines, that fits in function world, right? So solving the system of linear equations means finding the one x and y that you plug into both equations to make it true, or graphically, where do 2 lines intersect? Now, if you have 2 lines, they either intersect once at that point xy, they don't intersect ever because they're parallel, or technically they have an infinite amount of solutions because the 2 lines are the same. Now, hopefully you can tell here I gave a very, very simple system. Both in mx plus b form, you have the same slope but a different y-intercept. So hopefully you can see here that we are actually dealing with case 2. Right? I don't need any algebra, but I just want to demonstrate that when you have an equation, now I don't have it in the general form we've been working with the x's on one side and the y's, but I could do that. But I do want you to recognize that I have y to the first, x to the first, and because all the y's are lined up vertically and the x's are lined up vertically, I can just use the add down method, right? Linear combinations is the add down method, where I like to negate every term first and then add, because I make less mistakes when I add than when I subtract. Y plus negative y is 0. 2x and negative 2x is also 0. And then 4 and negative 5 is negative 1. So in this case, both my y's and my x's dropped out, and I got a false statement, meaning that the point of intersection I was looking for doesn't exist, therefore I must have parallel lines. So my solution set is empty, right, or null set. On Friday, we will have IB5 in partners, and our unit test, remember, will be on Thursday, May 31st, no calculator. So here's a graph of the 2 equations that I just gave you, and you can see, yes, indeed, they are parallel, slopes of 2, y-intercept of negative 5, y-intercept of 4, they're never going to cross. Now, what if I had negated one of those? If I had negated one of those, right, and I had, oops, sorry, if I took a negative and made one of these, right, took this negative and made one of the coefficients negative, what would you have? You'd have y equals 2x plus 4, and you'd have y equals negative 2x minus 5, meaning I do have an intersection point, and to find it, I still negate everybody, add down, x equals, negative 9/4, which of course is negative 2.25, right? Because that's negative 2 1/4. And then if you find an x point, how did I get this y point? You take x and you plug it back into either equation. It matters not. 2 times negative 9 fourths plus 4 is equal to y. Negative 9 halves plus 8 . Did I do that right? Negative 9 halves plus, plus 4, dippy. 4 is not 16 over 2. 4 is 8 over 2. And therefore I get negative 1/2. So when x is negative 9 fourths, y is negative 1/2, that point x, y satisfies both equations. If you were to plug that same x and y into both equations, you'd get truth. And when you graph, that is the point that lies on both the lines, right? So why would I bother going through this, Algebra 1? Because you need to take this same process, and that's why in Algebra 2 I still reviewed this process, because this process doesn't change, just gets uglier when I leave a system of linear equations and just say I want to solve a system of any type of equations. And of course, in not just any one, here we're going to use conic sections. So what is our objective? Our objective, solve systems of conics. So look at this system. What's different about it, right? Hopefully you can see. Now notice I've done a couple of things, right? First I'm like, this is not linear. Notice that I wrote that 16 as 4 squared. I did that on purpose, right? Here's what those look like. Hopefully you can tell that the first one, right, this is a circle, right? A and C are equal to each other, neither one equal to one, and this is R, the radius squared, right? So here's a circle of a radius 4 right here in red. The next one, this is the graphing form of an ellipse, right? Where Rx is 4, but Ry is 2, right? So that is not a circle. What is that? An ellipse. Now graphing this is swell, and I can see that how many points of intersection do I have? Right? That's not necessarily these two. I made a mistake. I was just trying to show you that if I have a circle and ellipse, I have lots of different possibilities, right? I have a possibility where I have 4 points of intersection, but it doesn't have to be 4, right? There's those 4. That might be true. But you might have an ellipse that only intersect once, intersect 3 times, intersect twice, right? Those two ellipses look kind of circular. You're never going to have the case, and it's just the geometry where you have kind of like, some kids always ask me, well, what if, is this ever, like these points of intersection going to be like more than one point? In other words, do they truly just intersect at a point, or is there some places where more than part of the curve matches? And the answer to that is no. These are going to be discrete points. Of course, I might not have any intersection at all, right? So, how do I solve this system? Today, we're going to use the add-down method. Even though it's not linear, I can't call it linear combinations, I can still use the add-down method. That we're going to do today. Tomorrow, I'm going to show you substitution. There's a reason why you learn both methods in Algebra 1, or you're supposed to. The add-down method is usually nicer algebraically, right? So The nice part about this, usually the algebra is nicer, but the downside is there's some restrictions of when I can use it, and I'll show you what those are. Maybe you can already think of it. Substitution, there's no restrictions. I can always use substitution. What's the downside? The downside is that oftentimes the algebra is messy. Okay? So on the test, I'm not going to tell you how to solve it. You're going to have to decide, do I use the add down method or do I use substitution? I don't know why those just went all over the place. Regardless of the method that I use, my goal is to eliminate all the x's or eliminate all the y's, which either method. Eliminate the x's or eliminate the y's. And that's the same as it was in Algebra 1. So here's my example, another example. That previous example was just, I was just trying to show you something to look at, what the system might look like. Here's the example that we're actually going to do. So example 1. Right? And the directions would say the following. The directions would just say, solve the system. You're supposed to recognize it's not linear. And you're supposed to know what the word solve means. It means to find. Solve means find points of intersection. Step 1, I generally like to name the conics so I have an idea of how many intersection points I want. Man, this is so weird. My animations are kind of weird here. Here is the restriction for the add down method. Do you only have squared terms? In other words, I have an x squared but no x to the first. Or I have a y squared but no y. If that is true, I can use the add down method. And I want you to look at this example here. Notice that I have a 4 and a 1. This is an ellipse. There's no linear x's or y's. The next one has a linear x. Notice I did this on purpose, trying to fool you into thinking these were both circles. They're not. This is a linear x and a y is squared. There's no x squared. If there's no x squared but a y squared, what is this? A parabola, right? A is equal to 0. A here, A is not equal to C, but they both are positive. Here, A is equal to 0, so it's a parabola. But notice that I've got y squared terms here. I only have y squared, and I have no linear y's. I do have an x squared and an x to the first, but that's okay because I have a y squared and I have a y squared but no linear y's anywhere. If you notice, the y squareds already have opposite signs, so I can add down here. Now don't tell me that's 8x, right? 8x squared, 4x squared, and x to the first are not like terms. You can't put them together. All you can do is write them next to one another. Notice the y squareds go away. I've just terminated one of my variables. Notice I've only got x's left. I have one equation, one unknown. When I have, yeah, that's right, here comes Algebra 1, back to bite ya. You have a squared and a linear x. You need to get everybody on one side and factor. I don't have a calculator. This is a math book problem. If I've taken away your calculator, all these are going to be nicely divisible by the leading coefficient. Yes, you're going to have to factor. You will not have time for the quadratic formula on this test. Now, in real life, yes, these are all, these could often be nasty coefficients, and I would use the quadratic formula, but I would give you a calculator to do that. So I have two potential points of intersection. One where x is -5 and one where x is 4. Remember what we did in the warm-up. If I want an x, if I want a y and I have an x, what do? Take this x and put it back into one of these equations. Now I think I'll put it in this equation since x is only to the first. Why put it up here if I'm going to have to square x, right? So I'm going to say 4x minus y squared is equal to -20. 4x minus y squared is equal to -20. And I'm going to plug in -5 and 4. And what do I get here? -20 minus y squared is equal to -20. I think I'm going to move the y squared over here to make it positive. And I'm going to add 20 to both sides, meaning y is plus or minus 0, but that's just 0. So when x is -5, y is 0. How about when x is 4? Again, I'm going to move the y squared over to the right side, add 20, and shocker, I get 36. Y is not just equal to 6. Y is equal to plus or minus 6. So how many points of intersection do I have between this parabola, right? This is a parabola, and this ellipse. How many points of intersection are there? 1, 2, and 3. 3 points of intersection. Good? Oh, no, I didn't. Okay. Here's example 2. Example 2, let's see what we have here. X and y are the same and have the same sign. This is a circle. So A and C are equal. I have a circle. A is not equal to C, but they have the same sign. This is an ellipse. I don't know whether it's horizontal or vertical right now. I didn't get it in graphing form, and I don't need to get it in graphing form. But a circle and an ellipse might never intersect, might intersect 4 times, 3 times, 2 times, 1 time. So here's the question. I've got x squareds in both equations. I have y squareds in both equations. I have a linear x. If I also have a linear y, I can't use the add down method. But I have no y to the first. Right? I have x squared and x to the first. I have a y squared but no y to the first. Therefore, I can use the add down method. So let me back up and then go this way so that I erase. That's how I can erase on my Mac. All right, so I can use the add down method. But if I just add down right now, I'm going to get 6x squareds and 10y squareds. That's not eliminating, right? But what if I multiply every term by -9? Do you see what I'm doing there? Multiply every term up here by -9. That's legal. Every term by -9. And that's what I have. So I multiplied the top equation by -9. Now I can add down. Do you see why? what's going to happen when I add down now? I'm going to get negative 4x squared. The y's are going to cancel out. The 144x to the first didn't have anybody to combine with, so it's just here next to the negative 4x squared. And then 351 minus 169, I'm sorry, plus 161 is 512. Factor out a negative 4, bring the 512 over, factor out a negative 4. Right, so what's the step in between here? I had negative 4x squared plus 144x minus 512 is equal to 0. And then I'm going to factor out a negative 4. I don't really need to do this, right? I'm just going to divide everybody by negative 4. I could have done that in one step. And when I did that, right, I divided everybody by negative 4. I just got x squared minus 36 plus 128, which I factored nicely without the quadratic formula. And I got x is equal to 4, or x is equal to 32. If you have an x, remember, when the directions say solve, you know that means you're looking for points of intersection. So you need to take the x is equal to 4 and 32 and plug it back into one of the equations. Gee, which one are you going to plug back into? I would do the one with the least amount of terms, right? So here I am with my 4 and my 32. I went to the equation 5x squared plus, because it just has least amount, and I'm going to put a 4 into there, and I'm going to put a 32. Right? Took the 4, put it in for the x, take the 32, put it in for the x. Now these numbers are a little high. I would give you a, I wouldn't, the numbers on the test might be high, but probably not this high. You're not going to be squaring 32. So notice that what I did here, 4 times, right, 4 squared is 16. 16 times 5, subtracted, divided both sides by 9, and I got y squared is equal to 9. Y is equal to plus or minus 3. So here I'm looking for an x when y is 3, negative 3, sorry, and I'm looking for an x when y is 3. Oh, no, I'm not. Silly. X was 4. I made x 4, right? X was 4. So you could write this as 4 and plus or minus 3. That's legit. Now again, I would not make you do this without a calculator. But when I did this, 32 squared, I hope you know 32 squared would be higher than 161. Multiplied by 5 would certainly be higher. Look what happened when I got this equation. After I squared and multiplied and I subtracted, I got a negative. Negative. Even when I divide both sides by 9, I'm going to get y squared is equal to negative who cares. Whoops, sorry. To negative who cares. Right? When you divide both sides by 9, you're going to get y squared is equal to negative who cares. That's why this mad face is in here. What does this mean? I did all this work, right? And I got y squared is equal to negative something, meaning that when x is equal to 32, there are no points of intersection. So what that means is between this, right, we knew this was a circle and this was an ellipse, there are only how many points of intersection? 2 points of intersection when x is 4 and y is plus or minus 3. Okay? So that's it for the first part of solving conic sections, when you're just going to be able to use the add down method. So remember, your homework is 1, 3, and 11. no, 3, 7, and 11, use the add down method for all of them. 3, 7, and 11.